I'll try to reach level lines, but let me start really explaining what is this critical prewetting. I'll start with just explaining notation for two-dimensional Ising model. Okay, this critical prewetting will happen. So first thing is some notation for 2D Ising. Okay, so I assume that most of you are familiar with 2D, but Ising, but okay. Anyway, it would be a pity to lose you at this early stage. So I'm taking, say, box. Maybe it's like that. This is two-dimensional lattice. Z2. Okay, the box I'm taking lambda. The way I'm putting it on the top of horizontal axis, because the surface phenomena will be important, but anyway. So on this box, I'm taking plus boundary conditions. Okay? So it means that at each side here I have a x, I have something which is called spin sigma x plus minus 1. Okay, and my Hamiltonian, say h, let me keep here, h, say n plus of sigma will be just minus sum over all nearest neighbors. So the model will be always nearest neighbor. Sigma x, sigma y. I started. Okay. Yeah, and from this Hamiltonian I construct measure un plus sigma, which will be just e and maybe beta. Yeah, beta is important here. Beta of sigma. Okay. This is the measure. Two things which are important is that, okay, there's some beta critical 0, infinity, okay, and for beta larger than beta critical, we have two types of order parameters. So the order parameters, okay. One is something which is called m star beta spontaneous magnetization, and the other which is called tau beta surface tension. Okay, let me just briefly explain you what this, recall you what this two means. Okay, so for beta larger than beta critical, this, say, this spontaneous magnetization is just average magnetization. Is very close to m star. Beta, positive, okay. Order parameters mean that both are positive. Okay. So the average magnetization is shifted by boundary condition. And for this surface tension, the way to describe it is, for instance, that this probability plus beta, that here's the box. I'm just making picture. Hope this picture will be clear that I'm having a certain. I'm taking continuous curve gamma. I inflate it to put in the box, and I'm asking about probability that there'll be kind of line with pluses on one side and minuses on another side. It's like creating island of minus phase inside. Okay, and this will be roughly E minus n integral of tau beta nsds. Okay, is it clear what I'm saying? So probability of creating an island of minus phase inside the box with plus boundary conditions, okay, is asymptotically given by surface tension, by integral of the surface tension. Okay. The reason I'm introducing surface tension because it will play a role in limiting object for these things. Okay. So these are just notations. It's fine. The questions here because
you might want to say that tau beta is a function.
Tau beta is a function of direction. Okay. Tau beta is a function of direction. Now, okay. So now the second thing is wetting. Wetting, let me show the same box, but now I'm making a slight modification of this picture, minus n. Okay. Modification, there are two modifications. First of all, instead of putting plus boundary conditions here, I'm putting minus boundary condition on the bottom. Okay. Second, in principle, I'm modifying a little bit interaction. So interaction between nearest neighbors in the bulk or between nearest neighbors here, it will be still 1. Okay, but interaction with the bottom is some h 0, 1. Okay, and then h here is some number. H here is some number between 0 and 1. So I'm doing two things. I'm modifying boundary conditions. Okay, and I have a special interaction with the bottom here. The physical way to think about it is that you are putting certain substrate, certain material on the bottom, and this material has different preferences between pluses and minuses. That's a simple way to model the situation.
So the H is a coupling constant?
H is a coupling constant. So coupling with the bottom is, you think about some material being in the bottom here. Okay, clear, yeah? And then with this I'm constructing, of course, so I'm constructing modification of this Hamiltonian, which I can write plus minus here, and I should put here h, okay, of sigma, and this will be again minus. So I can write down this coupling constant jxy, which is either 1 or it is h, as I described here. So I'm writing here, it will be this j xy of h sigma x sigma y. Okay, and then again minus boundary conditions. So this will be a Hamiltonian. One can construct probability measures n h plus minus. And again, beta, where is the beta? Here, plus minus beta. And I'm taking always beta larger than beta critical, so there are two phases. There's surface tension, and ask what happens. Okay, and then it's effect, or its theory, which was developed by, I think, Fröhlich and Pfister sometimes in the 80s. Okay, and that tells you that there's some wetting value of HW, which is really between 0 and 1. Okay, and such that that if H is larger than HW, then the typical picture you see in this box will be that there'll be, okay, so you have plus boundary conditions here and minus boundary conditions here. So there'll be always a line with pluses and minuses on both sides, which is kind of phase separation line. So the typical phase separation line in this case, so will go square root of n. It will be repulsed. So you have plus phase, and here it will be kind of minus phase. This is called complete wetting. Complete wetting. And for H less than HW, there will be something which is called partial wetting. Okay. The picture will be like that. You really have something, but this something will stick. Okay, and this distance will be of order 1. Okay, so this is the fact.
Does it depend on data?
Yeah, of course. This is HW. Okay. The exact value of this H wetting is known. That's the only contribution of exact solutions to this business. All the rest, what I'm saying, exact solutions are absolutely helpless and useless.
In the complete wetting, that curve comes how far?
It's repulsed. So the right way to think about curve is in terms of random walks. Square root of n.
Square root of n.
Yeah. As I'll explain, the correct way to think about phase separation lines is, of course, in terms of random walks. So it's just like repulsed random walks. There's entropic repulsion. Okay. Exactly at HW. What happens exactly is known if you really take random walk instead of Ising separation line. And then the scaling limit to, I think, this will be a scaling limit to absolute value of, it will be repulsed. It will be repulsed, but there's some information about scaling limit. Okay, what happens in Ising case, that's exact value. I also think it's repulsed. Yeah, it is repulsed, but okay. Whether it should be square root of n also. Okay, so now let me tell you, so critical prewetting. Okay, so critical prewetting, you see, I'm taking H larger than HW, it doesn't matter, for the rest I'll take H equals 1. H equals 1. Okay, so here's the picture. Again, plus, 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 minus. But now I'm taking lambda larger than 0, something which is called bulk magnetic field. Okay, and I'm considering yet another modification of this Hamiltonian. I'm adding bulk field to it. So I have minus H, and here we have n and 1 lambda plus minus of sigma. It is just like and 1 sigma, but also now I'm putting lambda sum over x sigma. Okay, so field has a preference for plus spins, right? Meaning that minus phase becomes unstable. Meaning that the picture should be really of that sort. Okay, it's phase separation line. There might be overhangs. Okay. The question of critical prewetting is the question: what happens when? So what happens? Question: what happens when lambda goes to 0? Okay. What happens at lambda 0? We know the interface flies up. Okay. So the issue is when you fix lambda small, okay, how it exactly diverges. The whole terminology of critical prewetting comes from statistical mechanics. There's a continuous divergence of this height. Okay, and specifically, so if I denote this gamma lambda typical interface or random interface in this model, so I can write this mu n 1 lambda beta plus minus beta. I keep it like that. Plus minus beta. This is probability measure. So, and I denote this typical size as d of lambda. So there's question 1 is size d of lambda, and question 2 is scaling for gamma lambda. Okay. So Let me explain you what is size of d of lambda. No, explain, just give some intuition. Proving exactly for Ising model, it's still an open problem. Okay, and but yeah. So I forgot to say, so all what I'm saying here is based on joint works with Seny here, with Ivan Vilenik and with Vitaly Vachtel. Okay, so results on Ising model, I'll tell, will be in the form of conjecture or results in progress, but I think we're beyond the summit. But anyway, so intuition for d lambda being, or for the lambda minus 1/3. Okay. Intuition here is random walk. Instead of Ising interface, think about random walk. This intuition doesn't solve problem for Ising walk, because solving problems for Ising model is proving that interface is random walk. Okay, that's a real issue of all the theorems one is doing there, and that's the most difficult thing. But as an intuition, it works well. Let's think about random walk. Okay, let's think about random walk. So we have random walk on certain level, lambda, say to power minus alpha. I want to understand alpha. There's a wrong phase. There's a wrong phase below this random walk. Okay, because I have magnetic field lambda which likes plus spins, below interface are minus phase, right? So actually we have here, if this is gamma is the path of random walk, okay, there's a penalty E minus lambda times area under this path, right? Just for wrong phase. And now let's think what it costs for random walk to stay on the height lambda minus alpha. The cost is entropic. The cost is entropic. You pay, one pays unit price each lambda minus 2 alpha. Yeah, just by diffusive scaling. Okay? So it means that entropy price per unit length is what? It is really lambda to the power 2 alpha, right? And energy price per unit length is lambda 1 minus alpha. You pay lambda, so the height is lambda 2 pi minus alpha, so it's lambda 1 minus alpha. Lambda times this, yeah? Okay? So energy per unit length is lambda 1 minus alpha. Okay? You compare two and you see that this is okay. This what it should be. This is balance between two things. Okay. Now let me formulate a result for scaling of this gamma lambda in order to. When did I start? 25, yeah. So I have 20 minutes. Okay, so in order to formulate results, I need still to introduce two things. Okay. Just in order to formulate conjecture. So let me. Okay. You see, so D. Conjecture for work in progress. Okay. So first thing I want to introduce is, Patrick still permit me, is Ferrari-Spohn diffusion. And this is connection to KPZ here, okay, which is perhaps a relevant picture Ferrari and Spohn considered some 12 years ago. Ferrari-Spohn diffusion. Okay, with parameters, let me call it, say, sigma square and q. And q is a function on half line, okay, which grows to, so this is q, grows to infinity. Sigma square is just a number, okay. And one considers, say, something L, sigma square q, which is 1/2 d2 dx square minus q of x on L2 R. Sturm-Liouville operator. It's nice because q going to infinity. I may assume some smoothness or regularity, doesn't matter, but it has compact resolvent, okay, and it has discrete family of okay, eigenvalues, discrete spectrum. So phi 1 larger than 0, let's see, leading eigen function. Okay, and then zero boundary condition. Zero boundary condition. Leading eigenfunction, and then the Ferrari-Spohn diffusion dxt is sigma dbt. And then it will be plus I think, sigma square here. Sigma square phi prime phi 1 xt. Okay. Or if you wish, I'm making dupe transform of this operator with phi 1 and build a diffusion from that. Whatever. Okay, this diffusion lives. And this diffusion, of course, has invariant measure. Invariant measure phi 1 square, density of invariant measure phi square. It's the first thing I need. Okay. The second thing I need wolf shape. Wolf shape, or equilibrium crystal shape for this tau beta. Tau beta surface tension of Ising model. Okay, and this is okay. Let me make a picture. K beta. So I'm taking direction x. Point h, so h is just tau beta for this. The other way to say it that tau beta is support function of this k beta. Or if one minimizes this sort of expressions, then optimal isoparametric profiles are rescaling of this k beta, as you wish. Okay, that's why it's called equilibrium crystal shape. Okay. So this is the notion I need. Okay, so we are talking about interfaces here, which go in horizontal direction. So maybe I'll have specific notation for this point here. Okay, and let me denote k beta is curvature of this wolf shape at h beta. Okay, just curvature of wolf shape at horizontal direction. These are two things I need to formulate conjecture. Now let me formulate conjecture. Conjecture is the following. I'm in this picture, I'm taking gamma lambda, okay, lambda going to 0. And I'm making rescaling, a rescaling of just lambda 1/3, gamma lambda minus 2/3. Okay. So I'm rescaling time, space by lambda 1/3, following this sort of intuition Okay? And I'm diffusively rescaling horizontal component. Okay? And then this converges to, weakly converges to Ferrari-Spohn diffusion with parameters curvature of wolf shape at this direction. Okay? And second, I want this potential Q, which will be linear. It will be Airy with something which, okay, 2m star x. Okay, so scaling exists, scaling given by Airy Ferrari-Spohn diffusion, and so this is conjecture. This, you should object, even looking at this conjecture, because even this thing is not well defined, right? It's not so maybe let me make a remark. So remark. So I make a bit, I'm zooming this picture. Here's this phase separation line. Yeah? It looks something like that. It has overhangs and it's so this gamma lambda. Okay, it's not graph of a function. It's really two-dimensional curve. Okay, so remark this gamma lambda. Okay, is a two-dimensional curve. Okay, line, polynomial line, as you wish. Okay, so it's not graph of the function. This thing is not defined. So, okay. So question is how. Okay, and the answer after, so the answer is a theory of Ising interfaces, which I'll try to explain. The answer is whatever you do, it will work. Whatever you do reasonably, it will work. And I'll explain why. You can take lower envelope, you can take upper envelope. Whatever you do reasonably, which produces a graph and which stays close and approximates, this will work. It doesn't matter. All the differences will simply vanish in this scaling. Okay. So what I want to do now, I want to explain this result in a slightly more simplified model, but which has this feature of not being a graph. Okay, and this will be modeled when instead of Ising interface, I'm putting self-avoiding work.
So is it the case that if you have this line to the negative 2/3 window, it actually is locally a graph of a function? Is that what's happening?
No. I'll explain. No, it's much, the mixing is, this effective graph structure is a much stronger property. The model is massive. For beta larger than beta critical, the model is in a sense massive. And okay, so let me really make a comment on what is true about Ising. Okay, so there's just I want to okay. So way out here, way out. And this is existing theory of Ising in 2 dimensions up to beta critical. Okay, way out is that Ising interfaces they really have kind of bridge structure. Okay, it's just bridge. Bridge structure. And bridge structure means that that interface, it never looks like that. The typical interface, it looks like that. You can do something, but then it's. Okay, and if you interpolate through these points, you already see something like effective random walk. Okay. So the first theorem is that whatever happens up to exponential probabilities, Ising interface, they have many points like that. This picture, by the way, this is naive bridge structure. The functional or operational bridge structure is that when you break interface by something like that, by irreducible pieces like that. Okay. And that's also could be proved. Is it clear what I'm saying? Okay, so it's a fact which is much more robust than more delicate questions I'm asking here. And this says that on probabilities which are well beyond what we want to study, one can reduce attention to interfaces which have this diamond decomposition structure. For these interfaces, the notion of function is well defined, and whatever you use to approximate this interface, you'll end up with approximating this structure. Okay. Well, so let me try to explain you how this scaling should be proved in the case of self-avoiding walks. In particular, why this curvature of wolf shape becomes important. So now I can raise down this thing. Oh, maybe I'll go on. No, maybe I'll go on here. Yeah, right. It's not time yet. Yeah, I'll use this technology. Yeah, perhaps I even don't need time to raise things. Yeah, don't need to raise. A, B, C, D. So E. So self-avoiding walks. Okay. I'm making picture very similar to what happened here. Okay. But instead of really making Ising phase separation line, I'm taking gammas, self-avoiding walks, which are going from this corner, I don't know, minus n0 inside lambda n. Okay, and then the weight of this E will be like that. And here's the region behind this gamma, which, say, let me call area of this region A of gamma. So then I'm putting minus lambda A of gamma, and this will be my mu self-avoiding walk, whatever n lambda. Okay?
The absolute value of gamma is? E2 minus beta, absolute value of gamma.
Yeah, absolute value of gamma is number of steps, sorry, number of steps. Number of steps, and this is area behind. Okay? So first thing is at all whether this measure defined. Okay, that of course depends on perhaps on beta and lambda. Okay, and I'm taking here beta larger than beta critical self-avoiding walk. This is something which depends, of course, on lattice, and this is called connectivity constant of Z2. Okay, this is connectivity constant of Z2. Okay, right. For this Z, if beta is larger than connectivity constant, one can define. So, okay, I have to explain you what comes instead of surface tension. Okay, so one can define two-point function. Two-point function, say g beta of x, take 0, point x, one considers all self-avoiding passes going from 0 to x. Okay, and this will be just some of all gamma from 0 to x, E minus beta. So if beta larger than B critical, this is well defined. Okay, and then, okay, surface tension. Surface tension tau beta of x will be computed in the following way. Instead of this picture, you take nx. You take a point far away in the direction of x, okay, and you compute minus limit 1 over n log g beta nx. Okay, clear, yeah? So you just take a decay per unit length in a certain direction. Of course, it will be convex. It will be homogeneous of order 1. By lattice symmetries, it's even be a norm, whatever. Okay, and this what plays, so let me put it so. Okay, so important observation here is the way to characterize this wolf shape. Okay, so wolf shape. Again, this picture, now this K beta self-avoiding walk. Again, the same picture. If this is direction x, h, that h, x, tau beta, x. Okay. If you consider series h to sum over all x's, e, h, x, g beta, x, maybe so. Okay, that for this series, boundary of wolf shape is exactly radius of convergence. They converge inside, they blow up outside. You just see it from this asymptotics, right? Okay, if you take h outside this, that will produce something which is bigger than surface tension. Okay, so for this series, boundary of wolf shape, okay, is kind of radius. It's radius of convergence. Okay, it's a strange statement, but I hope it's clear what I want to say here. Okay, this has a very clear implications for renewal structure of renewal structure of the type I was mentioning above there. Okay, so let me make the picture like that. So I'm taking I'm taking point H on the boundary, and I'm taking a certain CH cone. Okay. 5 minutes to go. Okay, yeah. So let me just explain here. I have a certain cone CH, contains lattice direction and so on. Okay. So I'm in these pictures. If I fix direction H, these pictures are made. Diamonds are made from these cones. Okay. So I'm considering diamonds of that sort. This is CH. This is minus CH. Okay, and then their passes are constrained inside this diamond, irreducible. For this pass, I'm using H of gamma. Okay. This picture clear, so I have this pass gamma, and then of course I have length of gamma. Okay. So then probability, I can denote it beta H of gamma, which is E x of gamma minus beta. Length of gamma is probability measure. Okay, this is precisely given that I split passes into this irreducible pieces, which is renewal structure. That would be precise implication of having things here as Okay, radius of convergence. Okay, which means now see, if I vary h a little bit around this point, I can use the very same cone, which means I can use the very same family of irreducible passes. Which means that I have parameterization of boundary of this wolf shape around any h sitting on it. Okay, so. Okay. So parameterization okay, of boundary k beta sub okay around h is that expected value of this beta h measure of e g x of gamma. Okay, this is 1 if and only if g, h plus g belongs to the boundary. Okay. So important direction for me are directions which are horizontal. So let me make this picture. This is h beta, horizontal direction. Horizontal direction, everything is symmetric, so there's a nice parameterization of the boundary. Let me formulate it. So for this path, I can take symmetric cone. Okay, and for this path, let me call this T of gamma, this horizontal shift, and let me call a vertical shift y of gamma. Okay. So the formula which you get from here will be that this chi beta for self-avoiding walk will be expected value y square beta h over expected value h t. Okay. This is the formula, and then when if you look at the interface, at the effective random walk, which after all looks like that. Okay, and this is gamma I, and this will be T gamma I, and this will be y gamma I. Then you just see that the computations which you have for self-avoiding walk reduce to computations you develop for usual random walk, and this was done by our work with Senya. Okay. So this renewal structure sum geometry explains you why you have explains your reduction to the simple random walk case, and I think I have to stop at this point here because. Yeah?
Okay, thanks a lot.
Yeah.
So we have time for a short question, as our coffee is gone.
So, in this picture, like which you started from this wedding, can I also treat this as a random walk?
Here.
So it's in this case?
No, in this case, you are just repulsed, you don't see the wall anyway. So it's like Ising interface flying in the empty space. In this case, what you have here is ergodic Markov chain. And it's not done in all the cases, but in a sense and it does not, so there's a limit for this Markov chain. It will be composed with exponential mixing.
So if I understand correctly, this reduction to the simple random walk, it's proven for the self-avoiding walk, and you think it's true for the Ising model?
No. So for Ising, I can also do it, but for Ising, this I didn't have time to explain. Okay, for Ising, on the top of simple random walk, there are serious problems for Ising. Okay, for instance, if you have Ising interface like that, and you have positive field gamma, then this gamma can just make huge islands of pluses. under the interface. So there's a bulk which lives its own life. And controlling this, and if there are islands, it just destroys the whole theory. Okay? So one has to control this. Also, Ising interface per se, it's not, you get some structure, but the structure will be more like real operator. So there will be exponentially decaying potentials, but pieces will not be independent. One has to do something with this. So it's, there are plenty of technical questions. But
you were able to prove this result? Or?
This is conjecture and preparation. We will be able to prove this result, yeah. But no, I think it's the reason I'm announced it, it's really beyond the summit in a sense. We understand all the difficulty, we understand, but it's.
Okay. Well, let's thank Dima again.